Hello everyone, welcome to our online mathematical classes. I Shilpa Patro, Department of Mathematics, Narajol Raj College. So today we study about metric space. So first of all we define what is the definition of metric space and what are the motivations behind to define metric space. So we all know about the concept of distance between 2 points. If we take 2 points, say P and Q, then the distance PQ is always greater equal to 0. The distance is 0 if and only if the 2 points coincide. And the distance from P to Q, that is PQ, and the distance from Q to P, that is QP, both are same. If we take another point, say R, then we know that the sum of two sides of a triangle is always greater equal to third side, that is PR plus RQ is greater equal to PQ. In 1906, French mathematician Fréchet generalized this notion of distance concept for points to any arbitrary non-empty set by assuming three intuitively accepted concepts as axiom, and he formally defined metric space. So begin with definition. Let X be a non-empty set. Let X be any arbitrary non-empty set. Let D be a mapping from X cross X to R, set of all real numbers. If D has the following properties, first property is D of xy greater equal to 0 for all xy belongs to X. This is non-negative property. This is non-negative property. Second is D of xy, the distance of xy equal to 0 if and only if x equal to y. This is identity. Third is D of xy equal to D of yx. This is symmetric property. And fourth condition is D of xy less equal to D xz plus D of zy for all x, y, z belongs to capital X. This is triangle inequality. If the mapping D satisfies these four conditions, then we say that D is a metric on X. Metric or distance function on X, and the pair XD, that is the non-empty set X and the metric D, together we call metric space. Next we define some examples of metric spaces. So if we take x equal to set of all real numbers and D is defined by x cross x2 r plus by D of xy equal to mod of x minus y, then we show that D satisfies the previously four axioms. First property is, we know mod of x minus y is always greater equal to 0. That is dxy greater equal to 0. Second condition is dxy equal to 0 if and only if mod of x minus y equal to 0. This implies that x equal to y. Third condition is dxy equal to mod of x minus y. This is equal to y minus of x, that is equal to d of yx. This is symmetric property. Fourth condition is d of xy equal to, by definition, this is mod of x minus y. Now we introduce z, this, and which implies that x minus of z plus mod of z minus y as mod of a plus b is less equal to mod a plus mod b. So we have mod of x minus z equal to dxz plus dzy. That is, D satisfies the four conditions. So D is a metric on R. We called this metric as usual or standard metric. Usual or standard metric on R. Next example is example 2. Let x equal to R2 and D, the metric, is defined by D of xy equal to D of x1 x2 y means y1, as x or y are elements of R2 and R2 element are two real number pair, so y1 y2. We define this as x1 minus y1 x1 minus y1 square plus x2 minus y2, that is square, whole root over. Where x equal to x1 x2 and y equal to y1 y2 are two elements of R2. So next we show that D satisfies the four properties. So first property is D of xy is greater equal to 0, because this is something square, this is positive, this is also positive, sum of two positive number is positive and the root over is also positive. So by definition d of xy greater equal to 0. Next is d of xy equal to 0. This implies that d of xy means this quantity is 0. So this implies that this is 0. So x1 minus y1 that is square plus x2 minus y2 that is square is 0. Sum of two real numbers are 0. That means both these quantities must be 0. So x1 minus 1 equal to 0 and x2 minus y2 equal to 0. So this implies that x1 equal to y1 and x2 equal to y2, that is x equal to y. Conversely, we say that if x equal to y, then this component are same. This implies that this 0 and this 0, and that is x minus y equal to 0. So second condition is satisfied. Third condition is d of xy that is equal to x1 minus y1 that is square plus x2 minus y2 that is square whole root over. So this is equal to x1 minus y1 is equal to y1 minus x1 that is square plus y2 minus x2 square the root over. So this is equal to d of yx. Now we show the fourth condition, that is triangle inequality. To show d of xy, this is less equal to d of xz plus d of zy, where x equal to x1 x2 are elements of R2, y equal to y1 y2, z equal to z1 z2. So we let a1 equal to x1 minus z1, a2 equal to x2 minus z2, b1 equal to z1 minus y1 and b2 equal to z2 minus y2. Then d of xy becomes a1 plus b1 the square plus a2 plus b2 square the root. So we write this way: ak plus bk that is square, where k varies from 1 to 2 whole under root over, and d of xz equal to a1 square plus a2 that square whole to the power 1 by 2, that is equal to summation over ak square k equal to 1 to 2 whole under root over, and d of zy equal to b1 square plus b2 that square under root over, that is equal to summation over bk that square k varies from 1 to 2 whole root over of 1 to 2. To show that, we show that d of xy that is less equal to dxz plus dzy. So that is to show summation over ak plus bk, that is square, k varies from 1 to 2 whole root over of this quantity, this is less equal to summation over ak square k equal to 1 to 2 whole root over of half plus summation over bk square k varies from 1 to 2 whole to the power 1 by 2. Now we square both sides. We get squaring both sides. We get squaring both sides. We get summation ak plus bk whole square k varies from 1 to 2. This is less equal to summation over ak square k equal to 1 to 2 whole to the power half plus summation over bk square k equal to 1 to 2 whole to the power half whole square. So if we calculate this quantity, we get a square a plus b square, that is ak square plus 2 times ak bk plus bk square. So these two quantities are getting cancelled out. We get that ak bk, that is k equal to 1 to 2, this is less equal to summation over ak square k equal to 1 to 2 whole to the power half summation over bk square k equal to 1 to 2 whole to the power 1 by 2. Now, which is Cauchy-Schwarz inequality? Which is Cauchy-Schwarz inequality? So D satisfies the four properties. So D is a metric on R2. We say that D is Euclidean metric, or we say that D is Euclidean metric on R2. So next example, for if we take x equal to r to the power n and d is defined by d from x cross x to r plus by d of xy equal to d of x1 x2 order করে x of n and y is y1 y2 dot y of n. We define like similar way that x1 minus y1 square plus x2 minus y2 তার square dot 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 xn minus yn তার square whole to the power 1 by 2, where x are elements of r to the power n. So x has n component x1 x2 xn, y equal to y1 y2 y of n. So we can similarly check that D satisfies the four properties. So D is a metric on r to the power n. Here we also define D infinity. D infinity of xy equal to max of mod of xi minus yi 1 less equal to I less equal to n. So we check that d infinity is also a metric on r to the power n. So first of all, each xi yi is greater equal to 0 for all I. So max of this quantity is also greater equal to 0. Max of xi yi, where I varies from 1 to n, is greater equal to 0. That is d infinity of xy greater equal to 0. So our first condition is satisfied. Next condition is let d infinity xy equal to 0. This implies that maximum of mod of xi minus yi 1 less equal to I less equal to n equal to 0. If max of this all quantities 0, so it should be all quantities must be 0. So mod of yi minus xi minus yi equal to 0 for all I equal to 1 to n. So this implies that xi equal to yi. So this implies that x equal to y. Conversely, if x equal to y, then each component xi, yi are equal. So their mod is also equal to 0. So max of this quantity is 0. So d infinity xy equal to 0, we say that x equal to y. Third condition is d infinity x of y that is equal to maximum of mod of xi minus yi 1 less equal to I less equal to n. That is equal to maximum of mod of xi minus yi. This is same as mod of yi minus xi is 1 less equal to n. So this is d infinity of yx. Now to show the triangle inequality, to show d infinity xy, this is less equal to d infinity xz plus d infinity zy, where z is another element of Rn. Z is z1 z2 dot করে z of n. So we have mod of xi minus yi, this is less equal to mod of xi minus zi plus mod of zi minus y of I for all I equal to 1 to dot dot করে n. So there, if we take both side maximum, this also inequality holds. So take maximum of this, we get mod of xi minus yi 1 less equal to I less equal to n. This is less equal to max of mod of xi minus of zi plus mod of zi minus y of I varies from 1 to n. So this implies that maximum of xi minus yi 1 less equal to I less n, this is less equal to maximum of mod of xi minus of zi I varies from n plus max of mod of zi minus yi I varies from 1 to n. So this implies that d infinity xy, that is less equal to d infinity xz plus d infinity zy. So d infinity satisfies the triangle inequality. Hence we say d infinity is a metric on r to the power n. Is a metric on r to the power n. So on the same set R to the power n, we define two different metric. So on the same set we define two different metric, first d infinity and dn. So on the same set we define two different metric. Next example is, let X be any non-empty set. Let X be any non-empty set, and let D is defined as follows: D of x y, this is equal to 0 if x equal to y, and D of xy equal to 1 if x not equal to y. So we check that D satisfies the four properties. The first property is trivial from the definition, that is D of xy greater equal to 0, obvious from the definition. This is obvious from the definition of D. And second condition is D of xy equal to 0 if and only if x equal to y. This is also from definition we get. Now we show the symmetric condition, that is D of xy equal to D of yx. If x is not equal to y, this implies that D of xy equal to 1. If x not equal to y, then y is also not equal to x. So this is implies that D of yx equal to 1, that is equal to xy. If x equal to y, then by definition we get D of xy equal to 0. If x equal to y, then y is also equal to x. So D of yx is also 0, that is equal to D of xy. Next we show the triangle inequality, that is D of xy less equal to dx plus D of zy. So first, if we take the case x equal to y, this implies that D of xy equal to 0. So we can write this as 0 plus 0. This is less equal to D of xz plus D of zy for all z belongs to x. Case 2, if x not equal to y and z is element of x, then we have two possibilities: either z not equal to x or z not equal to y. So since if z equal to x and z equal to y, then we get x equal to y. This is a contradiction. So it must be the case that z not equal to x or z not equal to y. Let z not equal to x. This implies that D of zx equal to 1. This is equal to D of xz. So D of xy equal to 1. This implies D of xz, this is less equal to d of xz plus d of zy, as d of zy is always greater equal to 0. So that is, we prove that d of xy less equal to dxz plus dzy. So d is a metric on x. D is a metric on x. This metric we call discrete metric or trivial metric. Discrete metric or trivial metric on any non-empty set x. So any non with respect to discrete metric from a metric space. So there are so many examples of metric space. In next class we will discuss all other examples of metric space and how to define new metric space from old one and bounded metric space, and also we define open set, closed set, neighborhood of a point. We will discuss in our next class. Okay, thank you.